Welcome to The Debate. Today we're looking at a world where tech giants are building these massive data centers that require, hundreds of megawatts of electricity. They are literally looking to build next to nuclear power plants just to keep the machines running. And the wild part about all of this, the entire architectural foundation for these multi-billion-dollar exaflop supercomputers was originally designed to make video game pixels look pretty.
Yeah, it's pretty crazy to think about.
It really is. I mean, we've transitioned from the neat, predictable world of traditional sequential processors to this completely new era of massive, mega-scale GPU computing that powers modern artificial intelligence. So, the central question we are exploring today is, well, how do we interpret this new era of hardware architecture?
Right.
In Nvidia's current dominance arise from a visionary engineering strategy that deliberately transcended the physical limitations of computing? Or did they just, stumble into a ridiculously lucky architectural coincidence that they're now scaling up through sheer brute force power consumption?
And as veteran hardware engineers who spent, decades in the trenches of the x86 ecosystem, this is a really profound question. I mean, for years, we operated on this comforting rhythm, right?
Oh yeah, the good old days.
Exactly. Every 18 months, Moore's Law just handed us denser silicon. You didn't have to completely reinvent the architecture. You just let the fabrication plants give you faster transistors. But when that stopped, the industry had to pivot.
They absolutely did. And I will lay my cards on the table right out of the gate here. My position is that Nvidia engineered a deliberate, visionary paradigm shift.
Okay.
When Moore's Law hit that thermal wall around, 2005?
Yeah, mid-2000s.
Right. You couldn't just keep cranking up the clock speed on a single core without literally melting the silicon. And Nvidia recognized that the future of computation wouldn't be won by just, a faster sequential worker. So they aggressively bet their entire architecture on a completely new kind of computing machine.
A bet, sure.
A massive bet. A general-purpose parallel processing ecosystem. And they did this long before the artificial intelligence boom was anywhere close to a certainty.
Well, and from a hardware engineering standpoint, I argue that the modern AI landscape is built on an incredible stroke of luck. I mean, let's be real. The GPU was designed to compute millions of pixels simultaneously because rendering graphics is what we call an embarrassingly parallel workload.
I mean, sure, it's parallel.
It is purely parallel. And it was an isomorphic mathematical coincidence that neural network training happened to require that exact same structure. What we are seeing today isn't some elegant theoretical triumph. Taking this lucky coincidence and scaling it into synchronized data centers that demand gigawatts of power, that is fundamentally an empirical, iterative hack.
A hack? Come on.
It is. It is brute force masking the limitations of our current technology.
See, you're calling their dominance a lucky head start, but I think that completely ignores the physical and financial reality of the hardware they were building. Let's rewind to the mid-2000s for a second.
Okay, let's go back.
Nvidia could have remained purely a gaming company, but instead they created CUDA, the Compute Unified Device Architecture. This was this massive software layer designed to let programmers bypass the graphics APIs entirely.
Right, to write C code directly to the GPU.
Exactly. To write general-purpose code directly to those thousands of tiny cores. And they spent billions on R&D for this when there was zero guaranteed market. Zero. For years, the gaming division essentially subsidized CUDA as this rogue research project. That isn't luck. That is setting a trap for the future.
Let's unpack the reality of that hardware, though. Why did they build those tiny cores in the first place? We really need to talk about SIMD here. Single instruction, multiple data.
Right. The core of parallel processing.
Exactly. Because if you're designing a CPU, say, an old Intel Pentium, you're dedicating massive amounts of silicon real estate to control logic, branch prediction, huge caches. And why? Because it's trying to execute a very complex, unpredictable sequence of instructions very quickly.
Yeah, it has to guess what you're going to do next.
Right. But a GPU strips all that clever control logic away. It just fills the silicon with thousands of dumb arithmetic logic units, ALUs.
I wouldn't call them dumb.
Well, relatively speaking, they are.
Because if you want to shade 1,000,000 pixels red, you don't send 1,000,000 separate instructions. You send one single instruction, and you execute it across thousands of ALUs at the exact same time.
Exactly. And that architectural shift away from the heavy control logic is the key to everything we have today.
But nobody at Nvidia was sitting around in 2006 designing ALUs for artificial general intelligence. It was pure serendipity. Neural networks are just, multiplying massive matrices of numbers. It is the exact same SIMD math as lighting a 3D polygon.
The math is the same, yes.
And the timeline matters here. It wasn't Nvidia who looked at their chips and suddenly invented modern AI. Look at the famous turning point in 2012, when Alex Krzyzewski and Jeffrey Hinton's group in Toronto just blew the doors off the ImageNet competition.
Ah, AlexNet.
Right. Krzyzewski literally bought 2 off-the-shelf GTX 580 gamer cards, duct-taped them together, and wrote custom code to train AlexNet. Nvidia had the hardware in the wild for gamers. Academics noticed it accelerated their math, and that gave Nvidia a fortuitous head start.
Okay, I agree the mathematical isomorphism was a fortunate discovery, but look, if someone discovers penicillin by accident and then spends 15 years meticulously building the modern pharmaceutical industry around it, we don't just wave our hands and call their entire market cap luck.
That's a bit of a stretch.
Is it? If this were just about the physical silicon, AMD would be tied with them right now. I mean, AMD makes incredible parallel processors.
Oh, they absolutely do. Fantastic hardware.
Right. So why didn't they win? Because when researchers like Hinton's group started seeing the potential, Nvidia didn't just smile and go back to making graphics cards. They doubled down.
Well, yeah, they saw a market opening.
They built CUDA into a sprawling ecosystem over a decade and a half. They built the libraries, the debugging tools, the exact computational primitives that an entire generation of computer science PhDs learned to think in. If you're listening to this and wondering why no one can catch Nvidia, it's because Nvidia owns the language the researchers speak. That requires immense strategic patience, not just luck.
Strategic patience on the software side. Sure, I'll give you that. But we are hardware engineers. If CUDA is the software foundation, we have to talk about the physical reality of what they've built to support it. Because I look at the physical scaling of these modern systems, and I do not see elegance.
Really?
No, I see the absolute definition of brute force.
I completely reject the idea that it's brute force. I mean, if you look at the actual silicon packaging today, it is stunningly elegant. They have completely circumvented the traditional server memory bus, which had become, frankly, a fatal bottleneck.
By throwing money and heat at it?
No, by innovating. Let's look at the H100 chip. It doesn't just have standard ALUs anymore, it has specialized tensor cores.
Which are literally just ALUs explicitly hardwired for matrix operations.
They are far more than that. Look, a standard core takes multiple clock cycles to multiply 2 numbers and add them to a running total. A tensor core executes a full matrix multiply accumulate operation in a single clock cycle.
Right, because it's hardwired for one specific math trick.
It is a purpose-built physics engine for linear algebra. But the real magic, the thing that proves this isn't brute force, is the memory. In a traditional x86 server motherboard, pushing data from the RAM sticks to the CPU requires firing electrons across inches of copper traces.
Yep.
That burns massive amounts of power and takes forever in computing terms. Nvidia solved this with high bandwidth memory, or HBM. They physically stack the memory dies directly on top of the logic chip using microscopic silicon vias. You shrink the physical distance the data has to travel from centimeters to literally millimeters.
They had absolutely no choice but to do that.
They figured it out. Because if they didn't put the memory literally millimeters from the logic, those 16,000 cores would just sit idle waiting for data. It is not some grand philosophical leap. It's a desperate measure to keep the beast fed.
Desperate or not, it's brilliant engineering, and they didn't stop at the single chip. The old x86 model was to just sit around and wait for Intel to print a faster single die, right?
Yeah, and it worked well for a long time.
But the new model relies on networking. Look at NVLink. They take 8 of these massively parallel GPUs, link them together with an NVS switch routing chip, and they behave as one giant GPU sharing a unified memory pool at full speed.
At full speed, sure, but at what cost? And then they scale up to the pod level. A single DGX superpod has 32 nodes. That means 256 GPUs operating in perfect synchronization. They have essentially demoted the traditional CPU to the role of a mere traffic controller managing the network cards.
You cannot bring up a DGX superpod and then claim this isn't brute force. I mean, come on. In hardware engineering, elegance implies doing more with less, finding a theoretical breakthrough that makes computation fundamentally more efficient.
And HBM isn't efficient?
What we are doing here is realizing that a single piece of silicon cannot hold a massive language model, so we just throw more chips at the problem.
You talk about NVLink like it's a miracle. But NVLink is essentially high-speed duct tape.
Duct tape? Are you kidding?
I'm serious. It's a massive, power-hungry interconnect fabric required solely because the individual chips failed to contain the problem. Calling NVLink duct tape is incredibly reductive. You cannot string 256 GPUs together using brute force. The latency of standard networking would destroy the system. The training run would crash instantly.
Well, they use InfiniBand too.
Exactly! The engineering required to synchronize the clock cycles across hundreds of chips so they act as a single logical processor is a monumental feat.
A feat that requires astronomical power. Let's talk about the physical physics you mentioned earlier. The exponential scaling we are seeing, combining larger chips, packing denser racks, forcing faster interconnects, it is literally breaking the power grid.
It uses a lot of power, yes.
A single rack of these servers can pull over 100 kilowatts. We're talking about whole data centers needing hundreds of megawatts just to run, plus enormous liquid cooling infrastructure because air can no longer dissipate the thermal load. They are literally having to build next to power stations. That is empirical, iterative brute force. It is throwing raw materials, raw silicon, and raw electricity at a wall because we lack a more efficient theoretical model for intelligence.
Okay, the computational density requires power, I'll give you that. But you are completely underselling the theoretical breakthrough of finally escaping the von Neumann bottleneck.
Oh, here we go.
Let's bring John von Neumann into this. For decades, our entire industry operated on the architecture bearing his name, a sequential processor fetching instructions from a separate memory bank one at a time.
Right. The foundation of modern computing.
It's the CPU, but they are only allowed to read one page at a time, and the library, the memory, is all the way down the hall. It doesn't matter how fast they can read the page, the bottleneck is the walking time. That speed of light limit of shuttling data back and forth is the von Neumann bottleneck. What Nvidia has done with HBM, massive SRAM caches, and NVLink is systematically dismantle that bottleneck.
They haven't dismantled it, they've just widened the hallway with more copper and silicon.
They fundamentally changed the architecture, and von Neumann himself was not a dogmatist about sequential computing. He knew the serial architecture was just a practical compromise based on the vacuum tube technology available to him in, 1945?
Yeah, ENIAC days.
If you look at his later work, particularly his final unfinished book, The Computer and the Brain, he was asking a profound question. Why does the human brain, which uses incredibly slow, unreliable chemical neurons, vastly outperform our fast, precise, sequential machines?
And his conclusion was that the brain relies on massive parallelism.
Exactly. Massive parallelism and redundancy, which is remarkably physically identical to the hardware hierarchy of a GPU cluster today. I firmly believe that if von Neumann were looking at a DGX superpod today, he would be thrilled.
Thrilled? Really?
Yes. He would say, obviously, I was always waiting for fabrication technology to catch up with the mathematics of matrix multiplication. He would look at the attention mechanism in modern transformer models running across 10,000 synchronized GPUs and find it deeply elegant.
I will grant you that von Neumann would recognize his own fingerprints on the bottleneck problem. He definitely would appreciate the physical transition to parallelism, but he would be deeply unsettled by what is actually happening in those data centers.
Unsettled how? He literally theorized this exact structural shift toward parallel biological-style computing.
Because von Neumann was, at his core, a rigorous mathematician. He liked things to be theoretically sound. He demanded formal proofs. Modern AI hardware scaling is arguably the least theoretically grounded discipline in modern computer science.
We have the math for backpropagation.
But it is purely empirical at scale. We don't have a grand unified theory of how an LLM thinks. What do? We increase the parameter count from 7 billion to 70 billion. We add another 1,000 GPUs to the cluster. We pump another 10 megawatts into the cooling system. And hey, the loss curve goes down, the model gets smarter. But we cannot mathematically explain why scaling these basic multiply-accumulate operations suddenly produces outputs that look disturbingly like human reasoning.
But we understand the micro-operations perfectly. We designed the ALUs.
We understand the micro-operations, yes. We know exactly how two matrices multiply. What we do not understand is the macro emergence. Von Neumann spent his final years agonizing over the gulf between biological and artificial computation, and the reality of our current hardware approach is, frankly, eerie. We have stumbled toward brain-like reasoning results using a completely non-brain-like mechanism.
Non-brain-like? We literally just discussed how they both use massive parallelism.
Yes, but the human brain operates on roughly 20 watts of power, a light bulb. A modern AI training cluster operates on 20 million watts. Scaling a massive array of silicon graphics processors to multiply floating point numbers until they start writing poetry is an empirical hack.
It's an engineering marvel.
It does not equate to understanding computation in principle. Von Neumann would look at this trial and error approach and demanded total redesign from first principles before he trusted a system where we are just turning the dial on the power grid without knowing why the ghost appears in the machine.
Well, I understand your skepticism about the empirical nature of the research right now. We are absolutely in an experimental era where the physical scaling is drastically outpacing our theoretical understanding of intelligence.
Exactly.
But I maintain that the hardware platform enabling that experimentation is a masterpiece of deliberate visionary engineering. Nvidia saw that the era of x86 dominance was ending. By taking the architectural gamble on massive parallelism, silicon vias for high bandwidth memory, and crucially, that 15-year R&D burn on the CUDA software ecosystem, they built the bedrock of the modern world.
It's a bedrock, yes.
They moved hardware design away from isolated, solitary chips and towards synchronized, room-scale supercomputers. That is not luck. That is engineering a new reality.
And I maintain that while the scale and the speed are undeniable feats of manufacturing, the foundation remains a fortuitous byproduct of the video game industry. The sheer empirical brute force required today, both in sprawling silicon real estate and massive power consumption, it leaves critical theoretical gaps.
We'll close those gaps eventually.
But right now, we have built an incredible exaflop engine for matrix math, but we are papering over our lack of deep theoretical understanding with raw electricity. Eventually, hardware engineers are going to have to bridge that gap. We have to figure out a mechanism that reasons without requiring a dedicated nuclear reactor, rather than just chaining another 1,000 GPUs together and hoping for the best.
Regardless of whether you view it as elegant vision or an incredible brute force hack, you've got to admit it is a staggering technological inheritance. When you step back and look at it, to even have this debate today, we are standing on an incomprehensible pyramid of human effort.
Oh, it is mind-boggling. I mean, to build a modern GPU, you need extreme ultraviolet lithography machines shooting lasers at 10 drops 50,000 times a second just to carve the transistors.
Exactly. We are resting on Claude Shannon's information theory. We are resting on von Neumann's original architecture. We are building on Geoffrey Hinton's decades of unfashionable neural network research when everyone else thought it was a dead end. We've gone from squeezing an extra megahertz out of a single core to watching Moore's law grind to a halt to this absolute explosion of parallel scale.
It is a profound privilege to be a hardware engineer watching this specific era of computing history evolve firsthand. The systems we are debugging today are beyond anything we could have responsibly predicted when we were worrying about thermal throttling in 2005.
It really is, and it leaves us and our listeners with a lingering question. As we watch these massive, synchronized data centers draw power from the grid, does the future of hardware lie in pushing this brute force parallelism even further into the gigawatt range?
Or are we destined to return to the drawing board to find an architecture we can finally mathematically explain?
Something to think about the next time you marvel at the silicon sitting on your desk.